I'll first introduce our model. So suppose you have a distribution over n times m outcomes represented as a probability matrix P. So the entry Pij is the elements of the probability of the elements ij. The samples are drawn independently from this distribution and forms a const matrix P hat. So the entry Pij hat will be the number of times the elements ij appear in the sample. So there are many practical problems captured by this model. For example, if you think each column corresponds to a customer and each row corresponds to a product, this Pij can be the probability that the jth customer buys the ith product. And in this setting, your observation will be a matrix of contains purchase histories. So the entry Pij hat will be the number of times the jth customer buys the ith product. Another example is the recently popular word embedding techniques. So for word embedding, your probability matrix will be a word-by-word matrix. And the entry Pij can be the probability that the ith word and jth word co-occur. For example, meaning they appear next to each other in some article. And in this setting, you can construct this empirical const matrix based on some large corpus. For example, all the articles from Wikipedia. I hope I've convinced you this model has some practical motivation. And now the problem is given much less than n times m samples, can you actually learn this probability matrix? Notice that this matrix has n times m entries. So with much less than n times m samples, you get a very sparse matrix. We are in this undersample regime. So it's natural to ask, with that amount of sample, can we actually learn this probability matrix P accurately? So without any assumption, this problem is simply estimating a distribution over n times m outcomes, which requires order n times m samples. So it's not possible to learn it. So we want to ask, is there any structural assumption we can make so that the sample complexity can be significantly reduced? Actually, for many practical problems, the probability matrix will be naturally close to some low-rank matrix. Can we leverage this fact to learn with much less sample? So almost all the problems in this model are still open. If we actually don't have enough sample to learn this probability matrix, is there any property that we can estimate? For example, eigenvalue entropies of P, and we can estimate. Okay. In this talk, I'll focus on the low rank case. We assume the probability matrix P has a non-negative rank K, and we're trying to recover P from the observation P hat. So this model generalizes a few well-studied problems. First example is community detection. So perhaps the most famous model in community detection is the stochastic block model. It's a random graph model, and nodes are partitioned into k-sets. If UV are in the same community, the edge between them exists with probability P, otherwise exists with probability Q. In this case, if you look at the probability matrix, this is an example with two communities. The top left block corresponds to the edges within the first community. The top right block corresponds to the edges between the two communities. This matrix is rank 2. In general, if you have K community, this matrix will be rank K. And the observations in the stochastic block model is a graph. So, and the graph corresponds to the empirical const matrix in our model. So actually, in the stochastic block model setting, your observation will be binary since you observe a graph. And in our model, the entry of the matrix can be larger than 1. However, for most interesting regime where you only have, say, n samples, actually the distribution of the observation will be very similar between the two models. So for community detection, your goal is to recover the community, and which is equivalent to estimating, to learn the underlying probability matrix in our model. And recent progress is trying to pin down the exact threshold for a sample complexity for approximate recovery, which is roughly order n sample in our model. Another example is learning k-topic model. So topic model is a generative model of text, and each topic has a distribution over words. This example, we have two topics. Topic P has a distribution P and a weight WP. A topic Q has a distribution Q and weight WQ. So this model generates pairs of words as follows. With probability P, the model draws two words independently from distribution P. And with probability WQ, it draws two words from independently from distribution Q. And our goal is to, and the goal of the topic model is to, given this pair of words observation, recover the topics. And previous work focused on recovery in the oversample regime. Again, in this case, if you look at the probability matrix, it will be rank K for a topic model with K topic. And the observation in this case is the bigram counts. Another related work is a learning hidden Markov model with K hidden state. So hidden Markov model, we have a hidden Markov model with two hidden states, and you have a bunch of observations. And your goal is to, given this observation, learn the hidden Markov model. And actually, in this problem, if you think about the co-occurrence matrix, so like the distribution between adjacent observation, the probability matrix corresponding to this co-occurrence matrix will be rank K if you have a hidden Markov model with K hidden states. And learning the probability matrix will be a useful step in learning the hidden Markov model. Okay, and we're ready to give the main theorem of our paper. So given an unknown n by n rank K matrix P, our algorithm takes a K times K squared divided by epsilon square times W mean squared sample, and learn the probability matrix P with L1 distance epsilon. So this parameter, n is the size of this matrix, and K is the rank, epsilon is the error. W mean is a parameter associated with this probability matrix. And in the topic model setting, it corresponds to the minimum weight of a topic. And two almost immediately corollary give us a learning algorithm for two topic models and two-state hidden Markov models with n over epsilon square samples, which we prove is optimal. So we also have strong matching lower bound for our algorithm. We show that for constant K and epsilon, our algorithm is tight in very strong sense. So it's already known that one cannot distinguish the case where the probability matrix P has rank 1 or rank 2 using less than n samples. What we showed is even stronger. If you have less than n observation from a hidden Markov model, you cannot distinguish whether you have IID sequence or actually the observation from a two-state hidden Markov model. So this table summarizes the sample complexity of three problems. One is learning, the other two are the property estimation and testing. So for the traditional setting, when you have IID sample from discrete distribution, learning requires n sample. But if you want to do property estimation, actually sublinear sample complexity is possible. Entropy requires n over log n sample, and identity testing only requires root n. So it's natural to hope for similar results for maybe hidden Markov model. Say like even for two-state HMM, can you estimate the entropy with sublinear number of samples? So unfortunately, our lower bound shows this is not possible. So this sublinear sample property estimation has given rise to the whole area of sublinear sample testing, and it's natural. So here now the open problem is what property does the setting need to have for this sublinear property estimation / testing is possible? Yeah. Okay, I'll briefly talk about the intuition behind our algorithm. So let's look at the most naive approach you can think about. We observe this empirical counts matrix, and you simply return a rank K approximation of this matrix. So for the uniform setting, when the entries of your probability matrix are roughly uniform, so 1 over n squared, and you draw n sample from this distribution, your empirical counts matrix will be very sparse. You look at each row, it will have a constant number of ones, and almost all entries are zeros, and you don't hope to find any 2. But we know that even in this setting, there will be some row with sum greater than log n over log n, which is by ball and beans. And yeah, actually, this heavy row will dominate the top singular vector. So your naive approach will not work. Actually, you need n times log n sample for this approach to work. So you may wonder, n over log n is not too bad. But for the non-uniform case, so in this example, the first row is much heavier than the other rows. So the sampling noise on the first row will dominate the top singular vector. And again, in this setting, you will need n squared samples actually for this naive approach to work. So how do we deal with this? It's worth noting that simply scaling by rows and column sum does not solve this problem. So if you're not used to thinking about spectral concentration, the one technical point you might want to take away is the following observation that has been discovered in different form by different communities. So actually, in the uniform case, the only problem prevent your empirical observation from concentration is the heavy rows. So if you can somehow prune the heavy rows so that they're no longer that heavy, actually your naive approach will work. In this example, we have roughly uniform probability matrix, and draw n sample, we get a sparse matrix, and we find a column which is abnormally heavy, and so we change some of the ones to 0. We prune this column, so they look normal, and we find another heavy column. We do the same thing, and we do the same thing for the rows. Then we perform truncated SVD, and this estimation will be accurate. But we still need to deal with the non-uniform case. So we deal with this by partitioning. We have this empirical counts matrix, and we group the elements together according to their empirical marginals. And for each diagonal subblock, we prune the heavy rows. Now we have spectral concentration in each of the subblock. And then we perform SVD on each of the subblock. For each of the subblock, we get K singular vector. And finally, we stitch all the singular vectors together from the subblock to form a subspace, and we draw a new batch of sample and project the empirical counts matrix onto this subspace. So this projection, because the sampling noise is high rank, so this projection significantly reduces the noise and also preserve the signal. So I will not go through our lower bound proof. I'd like to conclude with the future direction. So in our sample complexity, there is a dependency on W mean, which can be pretty bad. And probably it should not be there. So it certainly makes sense to remove such dependency. So it's not just interesting in its own sense. Removing W-mean will likely involve strengthening some known spectral concentration result for a non-homogeneous random graph. Another interesting question is to understand for what setting sublinear sample property testing is possible. Can we find some broad conditions such that it's strictly easier to test than to learn? And that's it. Thanks.
Any questions? Yeah.
So can you say anything about the higher rank cases, like beyond rank 2?
Yes, I mean the algorithm. So you mean the algorithm?
It's possible maybe you said it in the talk and I just missed it.
Yeah, our main theorem is about the general rank
So
K.
you do have a rank.
Yeah.